Hello students, AS level chemistry, chapter is atomic structure, lecture number 7. In this lecture we are going to talk about the third type of electronic configuration, that is known as electrons in boxes configuration. Now what are the three types of electronic configuration? One type of electronic configuration that is most common we write down in chemistry, it is SPDF notation electronic configuration. And second type of electronic configuration, it is noble gas core configuration, and this is the third type of electronic configuration, electrons in boxes. Also, we have studied that there are three different rules that we use for writing electronic configuration. The first one is energy rule. What is energy rule? That lowest energy orbitals are filled earlier, and if orbitals are degenerated means having equal energy. If orbitals are degenerated, they must be filled unpaired with parallel spin before pairing can occur to avoid interelectronic repulsion. This is the second rule, that is known as degenerated orbital rules. And the third rule that we are going to start with in this lecture, it is orbital rule. According to the third rule, each orbital can contain a maximum number of 2 electrons, and both the electrons, they must have always opposite spin. Now what we do whenever we want to write down electronic configuration in terms of electrons in boxes, we can represent an orbital by using three different styles. An orbital can be represented by a box, by using a circle, or by using a simple line. So these are three different ways by which we can we can denote an orbital. But obviously, as the name indicates, the box is the most common method for representing an orbital. That is why this is known as electrons in boxes configuration. Also, you people must remember, an orbital can contain 2 electrons. How we can represent, how we can denote electrons within these boxes, circles or lines? An electron is represented by an arrow. The arrows, they must have opposite spin. Means one electron is moving clockwise, other is moving anti-clockwise. Likewise, in case of circle, you can use these two types of arrows. But in some cases, what we do, instead of using complete headed arrows, we can use half headed arrows while writing electron in boxes. For example, this is another way for denoting an electron while writing electron in boxes configuration. So one thing you must remember, an orbital can be denoted as a box, circle or line. Second thing you must remember, electrons are denoted by using arrows, either complete headed arrow or half headed arrow. Both of these styles are equally acceptable. There is no problem whichsoever style you opt. Okay, now following this type of electronic configuration, we are going to practice, we are going to write down electron in boxes configuration for the first 10 elements in the periodic table. The simplest one is hydrogen. You know what is the electronic configuration of hydrogen? It is 1s1. Since there is only one electron and we always start filling electron into subshell S, and S from first shell it is filled first of all. So we can write down 1s1. But in this case, you must remember S subshell, it can contain maximum 2 electrons. So it means S can contain one orbital only. So what we will do, whenever we want to write down electron in boxes configuration in front of 1s, we will draw one box. And right now we are having one electron only, so we can draw one arrow. The direction of this arrow we can keep either clockwise or anti-clockwise. The first electron can be placed in any direction, there is no problem. So this is the electron in boxes configuration for hydrogen. Moving on, if you have been given helium, what change you will see compared to hydrogen? In case of helium, there are 2 electrons. So one as subshell, it is completely filled, and now since there are 2 electrons, both the electrons must have opposite spin. Now you can see in case of helium there are 2 electrons and they are having opposite spin. Likewise for lithium, electronic configuration is 1s2, 1s is completely filled, 2s1, 2s has 1 electron only. So what you will do, you will write on 1s, in front of 1s you will draw one box, this is for 1s, and you will place 2 electron because 1s would have 2 electron in case of lithium. Now 1 electron is left, that electron will be placed in 2s. So again, whenever there is s, s subshell can contain one orbital only. So in front of s we are supposed to draw one box only. So in this case this box would have one electron only. So electronic configuration of lithium is also completed, 1s2, 2s1. Now whenever you are writing electron in boxes configuration, no need to write down the power of s or p subshell. Simply you can write down 1s box showing 2 electron, 2s box showing 1 electron. Now for beryllium, even the 2s will be completely filled, so no considerable change, 1s2, 2s2. But as we will go for boron, its atomic number is 5. Now what will be its electronic configuration? 1s2, 2s2 and 1 electron in 2p. So when you will write down its electron in boxes, 1s in front of 1s, 1 box and 2 electrons. Opposite spin, 2s, 1 box and 2 electron. Simple. But when you are moving to 2p, now subshell p can contain 6 electrons. So it means there can be 3 orbital because an orbital is a pair of electrons. So subshell p, since it has 6 electrons, so that is why there are 3 pairs, there are 3 orbitals. One p orbital is known as px, one is known as py, the other is known as pz. All the 3p orbitals, they have equal energy, so they are known as degenerated orbitals. Why they have equal energy? Because they are at the same distance from the nucleus. So in case of p, always in front of p you must draw 3 boxes, and all these 3 boxes, they are at the same level, indicating they are having equal energy, they are degenerated. Now for degenerated orbital, what is the principle? The principle that we follow, it is that each degenerated orbital must be filled unpaired with parallel spin before pairing can occur. Right now we are having one electron, so we don't have any problem, we can place that electron in any p orbital. But conventionally what we do, first box is px, second is py, third is pz. So what we do conventionally, we start placing electron from px. So you can place an electron, you can keep the spin of this electron in any direction, first electron can have the spin either clockwise or anti-clockwise, that is not a problem. Now moving on for carbon, no problem. For 1s it would have 2 electron, for 2s it would have 2 electron. But when we will write down electrons for 2p, now carbon has 2 electrons in 2p. So that is why when we will draw 3 boxes and we are going to place 2 electron, first electron we will place in first box. Second electron, according to the degenerated orbital rule, it must be placed in the second box with parallel spin. If first electron is clockwise, the second electron in the next orbital must also be clockwise. This is according to rule number 2, that is degenerated orbital rules. Now likewise, when we will have nitrogen, its electronic configuration 1s2, 2s2 and 2p in this case would have 3 electrons. So in this case, each box, each p orbital would have 1 electron, and you can see the spin of all these 3 electron in different orbital, it is parallel, they are spinning in the same direction. This is in accordance with degenerated orbital rules. Now you can practice 2-3 elements yourself. For example, if I give you oxygen, write down its electronic configuration. Okay, if you have written, we do not have any problem for 1s, 2, 2s2. In case of oxygen, 2p has 4 electrons, 1s2, 2s2, 2p, 4. So what we will do, we will draw 3 boxes. First, 1 electron in each box. Now the fourth electron we can pair up in any one of the 3p orbitals, because now each orbital is giving equal repulsion. So you can start pairing in any one of the p orbital, but again remember, conventionally we start pairing by filling px. So we will pair up electron in the first orbital of p, in the first box of p. Likewise, now you can write down electronic configuration for fluorine 9 and neon 10. Okay, if you have written the electronic configuration, you can check it out. 1s2, 2s2, now 2p5, 1, 2, 3, 4 and 5. And for neon, 1s2, 2s2, 2p6. Simple? Okay. Now you have understood how to write down electron in boxes configuration. Now based on this electronic configuration, another information that I am going to tell you, this information is helpful in the subsequent lectures that we will discuss for atomic structure. Now what you must remember, looking at this electronic configuration, you must remember there can be 3 types of subshell. One type of subshell is known as completely filled subshell. Other type of subshell is known as half filled subshell, and the third type of subshell is known as partially filled subshell. Now for example, you know subshell S, it can contain 2 electrons. Whenever S has 2 electrons, we can call it completely filled subshell. Whenever S has 1 electron, we can call it half filled subshell. P can contain maximum 6 electrons. Whenever P has 6 electrons, like neon, P is completely filled. Whenever P has 3 electrons, like nitrogen, P is known as half filled subshell. And if P is having any number of electrons other than 6 and 3, it is known as partially filled subshell. So P1, P2, P4, P5, these are partially filled subshell for P. For subshell S, we cannot have any partially filled, either we have S2 or we have S1, no other possibility is there. Likewise for D, can you guess what will be completely filled subshell D? Yes, it will be D10. What will be half filled D subshell? D5. And what can be the examples for partially filled subshell D? D1, D2, D3, D4, D6, D7, D8, D9. So now you have become able to identify what is a completely filled subshell, what is a half filled subshell, what is a partially filled subshell. And now you must also become able to decide that which type of subshell is stable and which one is unstable. Always remember, completely filled subshell, they are most stable, and whenever an element has completely filled subshell, it is unreactive, it is least reactive. Like noble gases, group 8 elements, neon, it is inert, unreactive. Why it is inert or unreactive? Simply you can remember at this level that since neon has completely filled stable subshell. Compared to this, nitrogen has half filled subshell, nitrogen is stable, and those elements which have partially filled subshell, they are always least stable or they are unstable, so they can react quickly. So always remember, by looking at this type of electronic configuration, it has become very easy for us to predict whether whether an element is reactive or less reactive or inert. If an element has completely filled subshell, it is least reactive. If an element has partially filled subshell, it is most reactive. I hope you would have enjoyed this lecture. If you have any problem, you can give your feedback in the comments. Thank you for your time. Bye bye.